Okay, thank you for coming. As you know, but let's be clear about it, this is a course in differential geometry. I'm thinking now in a block of 4 lectures. Let me tell you what I have in mind. First of all, you have different backgrounds in the area of manifolds, so I'd like to briefly review manifolds. And what I mean by that, without any additional structure. So let me emphasize differential geometry. What it is manifolds plus structure. So let's review manifolds first without any particular additional structure. Very briefly. And of course this leads us to vector fields. Which I will formalize a little bit better than last time. And when you evaluate vector fields at one point, at a point being considered tangent vectors, and the whole space of tangent vectors is the tangent space at a point. So you all are quite familiar with this, but I think it doesn't hurt to review. And then a fundamental object of study at the beginning of just manifold theory is the tangent bundle, which is just formally the disjoint union of the tangent spaces. But it's fundamental that this thing has smooth structure, and it has smooth vector bundle structure. And the key word here, the headline, is defined by frame, defined by frames. And some of you in physics have heard the word moving frames and so on. That's what's going on here. A frame which depends on a point. So we're still in the setup of manifolds with no particular additional structure. And then we now go into really the differential geometry. And the way I see this is the first issue that needs to be dealt with is the notion of a connection. And a connection is something on a vector bundle, but in particular on the tangent bundle. On the tangent bundle. We will consider on many bundles, but in particular at the beginning on the tangent bundle. And we will formalize this. This will be formalized as a mapping which we call, using the classical notation, nabla. So in fact this is called nabla. I don't know why it's called nabla. I don't know anything about that notation except I use it in differential geometry. So nabla. Maybe you know, some reason in physics it's called nabla. Maybe it comes from mathematical physics, I don't know. So this is nabla. And this is a mapping from the derivations on our on the C infinity functions. So that's we will talk about this in algebra. This will be our ring of interest. I screamed at you last time that we should really look at the algebraic structures. So this is something called a ring, and the vector field is just derivations on that. But it's formalized as this algebraic structure, and it's a mapping to the first order differential operators on sections of the vector bundle. So I formulated this here. This is the module. You should really learn these concepts. I'm no big algebraist. My friend Ivan Penkov will tell you that guy Huckleberry is a bad algebraist. But I like to formalize things, seeing what's going on. You have the derivations, that's a vector field. What this thing here is a vector field. And it's a mapping from vector fields to first order differential operators on a function. Makes very good sense, right? You want to differentiate sections of the vector bundle and first order, not higher order. First order differential operators. Yeah. So the notation that we have here, you look nervous, but I'm going to be very precise about this. Okay. Yes. The notation is that if you have a vector field, which is in that's the derivations, it gets mapped to the operator nabla x. Yeah. And nabla x is a mapping from sections of the vector bundle to sections of the vector bundle, which is a differential operator. And differential operator means it works like a differential operator. It means nabla x of a function times a section. We talked this last time. Somebody made some money from me last time getting this right. It's the function times you derive the section plus you derive the function times the section. But of course, the derivative of the function is just apply the vector field to the function. Okay? So you see this all over physics? You have to agree.
Although, so last time you made a point about the Christoffel symbols, and you said,
yes.
But this is the connection. But then there seems to be a difference in terminology.
No, there's no difference at all in terminology, and I will explain it. Okay? What I'm going to explain. Ayman is asking about this connection to Christoffel symbols and so on. All Christoffel symbols, they arise when I take a basis. Okay, so I mean these things have bases, and once you take a basis, Christoffel symbols arise. Okay.
Okay.
Okay. And I will talk about that. So let me just. I'm glad you asked about this. Don't get nervous. So a basis. Well, no, a frame is Christoffel symbols that I wrote on the blackboard last time. These things are called Christoffel symbols. But please, I know this is very foreign to you to be so algebraic in a situation which is purely geometric or physical, but I guarantee you it's a good idea. These things occur in every subject of mathematics, including algebra, actually, algebraic geometry. And it's a very good idea to understand what the devil they are. Okay? So I will push that a little bit. So that's one of the goals, is to really formalize connection. And after that, I want to talk in detail about parallel transport. I'm just telling you now what I'm going to talk about in this block of 4 lectures. Of course, we'll talk about it. Parallel transport along a curve. Curves here are always called gamma. Smooth curve. Sometimes the curves are only piecewise smooth, but let's not worry about that right this moment. And the idea is this: you have a smooth curve going, say, from a point gamma at time t0 to gamma at time t1. And you have the vector field along the curve, at least on the curve itself, which is what we call gamma dot. That's the velocity vector field. This is all in a coordinate patch, so we can calculate. And you take a vector here at the beginning, and you want to know how to translate it parallel to the end. So you move it, and 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 you move it, parallel to the end. And what that means is, this vector is not changing with respect to the velocity vector. This means that the derivative of the moved, so maybe we call this y, we start at y0, y of t0, someplace in here we have y of t. This means that the velocity, that with respect to the velocity vector, this thing is really parallel. This is exactly the concept that we talked about before. Move by parallel transportation to the nearby fiber. Yes. Now we know if you can move over to that fiber, you can pull that thing back, take the difference, divide by h, and you have a derivative. Right? And using parallel transport, we understand how, in fact, the parallel transport, I'm going to prove this, parallel transport gives, as expected, as hoped, let's say, the connection. Okay. Now, that's the first thing that's really new for everybody in this room. The rest of it's a little bit of a review. Connection is the first fundamental thing that's new. Let me just add an additional remark that we will show, that it's easy to build connections. We'll see this by partition of unity. So that's not the problem. There are many, many connections. You have a remark? Might be good.
Oh, no, it's partition of unity.
Okay. Yeah. It's easy to build connections by partition of unity, and the full space C of connections, so maybe connections on the vector bundle E, is an infinite dimensional affine space. So it's a huge space. Okay. So I said at the beginning, we have manifold plus connections, but there are an incredible number of connections. And now you do have a remark, right?
Yes.
I think.
No, get finish your
No, go ahead. Yeah.
So I was wondering that
Are all connections created using partitions of unity, because that only makes sense when your manifold is compact, no?
No,
When it is
No, no. so,
When it's paracompact.
you,
it is always
paracompact, maybe you're thinking.
Manifold by definition is paracompact. Second countable manifolds are
Yeah,
paracompact.
okay, fair enough. So you always have that essentially. Yeah, I was just worried that if you can't do the partitions of unity, you won't have your.
Well, let me even be precise about it now, okay? So, if we have UI a covering of M, with some locally finite, of course, otherwise I would never consider it, probably, with chi I partition of unity, that's the usual situation. As he's pointing out, you need something for this topologically. Maybe you need paracompact, but for me, all of these things are paracompact. Okay? So, I never said it, but for me, a manifold is by definition paracompact. But not compact. Okay, not necessarily compact. Okay? So, partition of unity, and then, nabla alpha connection, or it's bad downstairs, let me call it upstairs alpha, connection on U alpha, that makes sense. Just to restrict the bundle to U alpha and so on, and now you can differentiate sections over U alpha. Then we define, let's see, I'll try to follow your textbook. I remember in your textbook, maybe you put something here, bar x, defined to be bar x of S is some chi alpha nabla alpha of S, okay, restricted to U alpha. Okay, so what's going on here on the right-hand side is nabla alpha of something on U alpha is okay. So I restrict that, and of course with a section you can just restrict it. And now I multiply, that's okay. And now this terminology here means I extend that by 0 to the full manifold. So that thing's globally defined, so that everything here is defined and you check its connection. Okay? So it's an interesting thing is there's a big Bourbaki warning. The Z in the road of Bourbaki is this: 1/2 of a connection is not a connection. You think you can just multiply by anything and so on, but it's quite key here that that's a partition of unity. Okay. You just check the rule of the derivation rule. You know what I mean by the derivation rule. Nabla of Fs is equal to what I just wrote there, right? You will see how you really use that's a partition of unity, and it's okay. So I mean, you see. And we will see immediately how on coordinate charts it's very easy to build connections. And in fact, most people in physics really just write them always down in coordinate charts. That's where you're seeing the Christoffel symbols and so on. So very easy, so we just glue these things together that we defined on coordinate charts. Okay, but I'm going to do this all. I just want to show you where we're going. I think I've said enough about connections, about where we're going. Connections. Okay. And now after this, I go backwards to Riemann. It's very interesting. I don't know the history well enough to even say anything really, but what I'm talking about here primarily is due to the Italian school in the Toscana, Ricci and Levi Civita. But long before, and I'm sure Riemann understood all of this in some mysterious way, Riemann introduced what I would call a bundle metric. Now this is really a new concept. I didn't talk about this at all in the previous lectures. I talked about the notion of connection a bit. But this would be the new thing I really want to emphasize in these lectures. And so you have some idea what this word might mean, and then I'll make it precise later on. Okay. You have a manifold M. You have over every point, you have this bundle over N, and you have over every point of this bundle is called E. Malta was very good in pointing out that pi is a mapping from a vector in the fiber here over the point x. So quite often I write Vx, and pi of Vx equals x, so it just maps it down there. This is a vector space. This thing is called Ex. Okay, that's the picture we always had. Of course, everything is smooth here. I mean, it's not just formal. Okay. That's all a vector bundle is. It's a bundle of vector space. Now, the question is, what is a metric? Now, the trouble is with this word metric, it has at least two meanings that are not the same. Okay, so I want to talk about it here. So recall, I just taught the beginning course in analysis. So recall analysis 1. All right, you have a set X, and you have something on x cross x to the non-negative real numbers, right? We call this thing a distance function. I actually prefer to call it a distance function than to a metric. Then there's no confusion. So let's call this thing a distance function. Distance. It has various properties, as you know. D of xy is 0 if and only if x equals y, and things like that. The d of xy. So things that anybody believes and thinks are completely trivial and more or less always is some symmetric thing, but the key thing is triangle inequality, right? So triangle. So let's call that a distance function. Some people call that a metric. Okay. By the way, these manifolds that I consider are all metric spaces in that sense. In the sense they have a distance function because they're paracompact and all of this stuff. Hausdorff. I mean, they're wonderful. As topological spaces, a manifold is just some beautiful metric space as a topological space. So we make a note here. Then M is a metric space in the above sense. In the sense that it has a distance function. Of course, not unique. Many distance. Distance is no problem on these manifolds. What's interesting is manifold plus. I forgot, that's like an advertisement on American television. Something plus. It's always something plus, right? I don't know what it is. What is it? Something plus. Oh, I know, toothpaste. It makes your teeth shine plus. I was just at the dentist, so. Okay, plus. So manifold plus, it has something more than just manifold. Something more than just manifold. And the more, the first, the Riemann's plus, is what we call a Riemann metric. Riemannian metric. Or I used to say a Riemann metric. No, Riemannian metric, let's call it. So it is not this metric we just talked about. That's the first thing I want to say. It's not that. Okay? Here's what it is. Here's what it is. So you start with an example. And he did start with an example with his teacher Gauss. So he started with the sphere. And he says, all we have in this manifold stuff is tangent vectors. So, for example, we have two tangent vectors here, say u and v, which are tangent to the sphere. Okay. Now, what are the only qualities you learn in high school? Everybody here went to high school. Even I went to high school. So, everybody here went to high school. And okay, let's transport these things and let's put them here so we can talk about them. U and v. And let's call this Fußpunkt 0. You see, I already transported it over here so I can talk about it. It's in a vector space here. And what are the only things you can talk about? Well, you can talk about geometric things. The only thing you can talk about are angles and length. Everything else comes from that. Angles and length. If you don't believe me, try to do Euclidean geometry. You need projection, you know, you have a triangle, you project, you have all these things. If you know angles and length, you know everything. Yes, ma'am.
So those are two different tangent vectors.
You have to be, so you know how I am.
So they're different tangent vectors, but are they to the same point or are they to different points?
They are tangent to the sphere at the same point. Does that answer your question? That's what I meant to say.
Yes.
I'm trying to simplify. You know, if you're a child and you look at the sphere and you see two tangent vectors at the same point, the child says, okay, let's move them over here so I can talk about it because I don't know what the devil to do there. So I moved it over there so I could talk about it. Okay? And then, of course, geometry, so somehow you need to know length and angles. And what you learn, of course, and everybody forgets to tell you at first, is you say, well, okay, here we go. This is A, U is AB, that's U. And V, I'll try to draw it in the same way. V is CD. Right? And then somebody tells you, well, the length, well, the length squared, square is better than not squared, right? So the length squared of u is a squared plus b squared, right? I always like to square because square root has a singularity at the origin. This angle here, of course, has an orientation somehow. I think from U to V. I don't know. You have to really worry about the orientation of the angle, right? And let me see here. If we take the scalar product of U with V, this is equal to AC plus BD. And that's the scalar product, right? And they might be too long, so we have to scale them, right? So maybe if we take the scalar product of U and V and divide by the length of, we make them unit vectors, right? You've done this in high school. We make a unit vectors, And is this cosine? What is this? This is cosine of the appropriately, this is cosine of that angle there, which maybe I'll call a theta maybe. Right? Okay. So what I tell you is about angles and length. And what is an angle? I don't know if you've ever asked these questions, but I sit at home like an idiot on paper and ask myself the questions of the order of magnitude, what's an angle? Yeah. So you say, what is an angle? And you say, what's an angle? Okay, an angle is that thing there. And you say, well, at least if it's in this quadrant, well, this is cosine theta, sine theta. And at least here, I mean, if we know theta, we know cosine theta and sine theta and so on, because sine theta is square root of 1 minus cosine theta squared. So all you need to know is that to know theta is a measurement of theta is cosine theta. It's the same thing. In some sense, right? It's in some sense the same thing. So angles and length are 1000%, if there's such a thing, determined by the scalar product. All. Right? Angles and length are determined by the scalar product. Okay. So what you learn here is the scalar product is the same thing as geometry. At least from this naive viewpoint, right? Right? At least from this naive, you asked me to define geometry, but I don't. Okay, it's a reasonable thing. Right? Well, Riemann, of course, knew that. But Riemann's whole point in this elementary discussion was, look, you don't really have any canonical basis. You don't have canonical coordinates. You don't have anything canonical here where you can define the scalar product, right? You don't have that. Even on a sphere, what are you going to take? Right? It's this whole thing again. That was Riemann's observation. Right? It's really some sort of amazing observation in that time of mathematics. So what is a scalar product? That's really the question. What is a scalar product? So let's call it, say B. Now let's see B. Maybe it's defined. Let's just be a little bit precise. This is a manifold M, and here's a point X. And the scalar product is defined at that point X, okay? It's defined at that point X. So where should it be defined? It's on the tangent space of X. Tangent space of X. To the well, what did Einstein have to say about this thing? Dimension 4, maybe this thing's not positive definite. Right? So let's make this a mapping into R. Yeah? Do you object? You better not object. I'll tell Mr. Schub. No, your professor is not Mr. Schub. It's Mr. Kletterman. No, who's your professor?
Both of them?
Both. Okay. I know Mr. Schub quite well, so I'll tell Mr. Schub, if you insist on that being the positive real numbers, then he'll be very mad at you. Right? There are vectors of negative length. So B, U, U, less than 0 is allowed, maybe. Right? There can be vectors of negative length. However, non-degeneracy should be required. Is required. When you have such a bilinear pairing, what does it mean, non-degenerate? It means what it means is nothing, no vector, except 0 is perpendicular to the whole space. So we have a vector space, we have a bilinear form of this vector space. I talked about the tangent space, it's a mapping of the real numbers. We look at the perpendicular with respect to V of this thing. These are the set of V such that this bilinear thing is 0 on the whole space for U arbitrary. There's a more sophisticated way of saying that, but it's geometrically clear. You don't want something that's perpendicular to everything. I like it in some of my mathematics, but at the beginning in geometry, you don't want something that's perpendicular to everything. If you have something like that, you call it degenerate. Yeah. It's called a degenerate bilinear pair. Okay, so what Riemann wanted to do, he wanted to understand what is this thing here. Well, let's see here what Riemann says it should be. Riemann says it should be bilinear. Bilinear. So that means linear in each argument, and non-degenerate. Okay. And if it's positive, it's the geometry you know about. Right? What is the statement that if it's positive, it's the geometry you know about? It is the statement that D is positive, implies more or less the standard geometry. Can somebody here make that precise for me?
Euclidean geometry? Euclidean geometry.
Good. So let's. Good. First step.
Up to an isometry.
Pardon?
Up to an isometry.
Talk louder.
Up to an isometry.
No. Almost. Any other ideas? More or less the standard geometry, yeah.
I mean, up to isometry is the same as your usual inner product.
Up to isometry, say it again, it's too quiet.
Up to isometry, you get the usual inner product.
Okay. That's more or less what he's saying, I think. You know, Rebecca. So, I would be talking like this. You can choose a basis. Yeah, can't you choose a good basis? Let me see. I don't bring in money today, but all this food. So I will owe you the money. Yeah. If I give you this vector in this geometry, see this vector? You see it, right? You have freedom to choose another vector, which is not this vector, and not just a dilation of this vector, another one someplace here, which as a pair gives the simplest possible thing you can think of with respect to this geometry. Would you do that? I wouldn't. I would do that. Wouldn't you? This is what these guys are talking about. They say, they go blah blah about after you take a coordinate change or something like this. It's the usual thing.
So you can find an orthogonal.
You certainly can find something perpendicular, right? It's just solving some stupid equation, right? However, can you find something of length 1?
So you're essentially saying that you have an orthogonal basis.
Well, we don't. If this vector is length 85 and this vector is length 10,047,
Scalar should doesn't change anything.
and you want to, okay, he's right. If this is 85 and 10,000 and so on, you can somehow,
Divided by its length.
you can, what are you doing when you do that? You're changing the metric. This, let's make it easy. This this is u. B of uu is 16. What's the length of this vector? 4. You don't get to change, but you can change b, right? You could change b and divide it somehow, you see. But what you can always do is get this orthogonal basis. They are eigenvectors of the symmetric matrix. I hope you know that a symmetric matrix in some basis, or a bilinear form, has eigenvectors, and that means it's going to be like that, but the length will be different. It might be this vector 4 and this vector 25. Okay? So you have to change, somehow you have to change it. Almost get it. Up to dilation. Wait a minute. Not just a stupid dilation. This one you have to dilate, maybe the change the form here by 4, and here you have to change it by 5 or something. You see what I'm saying? So it's a non-trivial change of the metric. I would say this dilation, which we call conformal, you dilate. Okay, it's like going from inches to centimeters. There's no difference. I don't know the factor, but you can compute it, right? So it's conformal, right? But if you have two different directions and it's length 20, you see what I'm saying? Okay. So more or less, I just explained. All right? More or less, but not exactly. Okay. And Riemann knew that. Riemann knew that we don't have any basis, and we don't have a canonical basis of. I hope you can walk in and say at Jacobs University I learned linear algebra from somebody, and I know that a bilinear form usually can have a good basis. That means it can be diagonalized with the appropriate basis in eigenvalues, vectors. If this form is positive, definite, that means all the norms are positive, right? The eigenvalues are all positive, but not necessarily 1. And the basis that you use to diagonalize depends on the form. Yeah? Okay, Riemann knew this, although he did not know what is a bilinear form, maybe. I mean, he knew, of course, but I mean, this whole algebra was not formulated until much later. It's Riemann. Yeah. You have a tangent space here and a tangent space there. You have two different vector spaces. You would like to say they're more or less the same, but somehow the metric is changing as you move. So Riemann said this. We go from the tangent bundle, and let's go to the bundle of bilinear forms. Well, any bundle. You have any vector bundle and the bundle of bilinear forms on that vector bundle. Have you got it? Yes.
Is the bundle of bilinear forms just a set of bilinear?
Okay, let's go through that. Let's go through it. You ask really good questions, but you need to ask yourself. You saw my new homework system. You're going to have to ask yourself these questions. It's good. Okay? So we have a vector bundle. It's better to think abstractly, not just tangent bundle or something kind of vector bundle. Each fiber is a vector space. Okay? Okay. Given a vector space, over the real numbers, everything here is over the reals. Okay? Given a vector space over the reals, you have the bilinear forms on that vector space. Right? if B1 is a bilinear form on that vector space and B2 is a bilinear form on that vector space, then A1, B1 plus A2, B2, where A are constants, and A1 and A2 are constants. You can add them and, yeah? Now, a big boy or a big girl remark about that is the space of bilinear forms on a vector space is a vector space. Right? Is a vector space. Right? So if you have a vector space over X, you have Vx. Oh, I called it Ex. By the way, the reason we use the letter E is the entire space. This is Steenrod's notation for a bundle. E upstairs is the entire space. In English, E, entire. The complete space. And he had B downstairs because it's the base space. So it's an entire space down to the base space. And the fiber over X is a vector space, Vx. And now we just make a new bundle. The fiber space over X is the bilinear forms on that vector space. Okay? You can imagine that if the vector space is moving smoothly, the bilinear form space is moving smoothly. Okay? Okay? Well, you got it. Riemann didn't quite have that notation, but it's not bad. You have the tangent bundle, for example, or any bundle over base space, B. And you can go over here to the bundle of bilinear forms. Let's call it bilinear, the bundle over the base space. Okay? Let's call, I don't know, I don't care about the notation. You just have the, yes ma'am?
Is it somehow related to, in a way, dual space of that space?
To a dual space? Yes and no. She introduced a new word for our discussion, and I'm going to follow your word a little bit, okay? And actually that word I haven't talked about enough. You all know if you have a vector space, I jumped to bilinear, that's a big jump. Let's just jump to the dual space. The dual space of a vector space is the space of linear functions, right? Linear forms. Not bilinear, there's only one variable. So you could have one variable or two variables. I jumped to two variables. But one variable is called the dual space. So if I have a vector space, I have its dual space. If I have a vector bundle, I have the dual bundle. Yeah? Of course. And if things transform here in some way, things will transform in another way here, you can figure it out. Same thing. If I have a vector space, I have the bilinear forms on that vector space. By the way, we will talk intensely later on about spaces of tensors. And instead of just talking about bilinear forms, we'll talk about tensors of all types. And it's very confusing. Right now, let's just start. And I'm glad you mentioned the dual space, because, well, maybe, yeah.
Yeah, I think we did cover cotangent spaces and calculus.
Yeah, but not everybody was there, so, yeah, okay? Well, most people were there. Okay? So we have the dual bundle and the bundle of bilinear forms. And now when you have this bundle of bilinear forms, what is the right object? Here's the bilinear forms. Here's the zero section. Now, what did we talk about last time? I hope you like my picture from last time. I don't have any colored chalk anymore.
There's some.
Oh, great. Thank you. Oh, the right object is this. Is a section of this bundle. Right? The right object in the bundle itself is a section. And the right object here is a section. Do you see what this section is doing? What happens is I move as the point moves in the base. You don't see it yet? Yeah?
Different value.
That's right. So maybe as you start here at the point x, maybe you go up here and then over x, and that, yeah? This would be a bilinear form x. And if you move x, maybe over here to x hat, you would have another bilinear form here in x hat. Yeah.
Do you require that it's non-degenerate at all points?
So we're getting to be interesting now. So you have a section, yeah? You have a section. So that means it's a moving family of bilinear forms. It means it depends smoothly on the base point. It's a section. Right? That's great. Now, one possibility here is that this thing is positive definite. Right? That's what you want in Riemannian geometry. And some physics guy over here who's bothering me says that this thing, okay, he's not a physics guy, he's just going to make it negative definite. The physics guy might have signature 1,3 in a bilinear form on R4, right? Got it? You know the physics form. We call it the physics form. X squared plus y squared plus z squared. That's the standard form, minus c squared times t squared. Maybe you scale it to x squared plus y squared plus z squared minus t squared if you scale it. Right? The speed of light should be 1 maybe. I don't know. Okay. That's a bilinear form. That is non-degenerate. That is someplace in this thing. Right? It's someplace there. Now you all tell me what happens here if I start over here at a positive definite Euclid. I start over here at x squared plus y squared plus z squared plus t squared. Right? Euclid loves that form. Some physics guy over here says this one is x squared plus y squared plus z squared minus t squared. What happens in between?
Be zero.
Hmm?
The form would be zero.
The form wouldn't necessarily be zero.
Yeah.
No!
So the eigenvalues are.
Okay, he's a big boy now. The eigenvalues are plus 1, plus 1, plus 1, minus 1.
Yeah, so one of them would be zero.
Aha!
Okay.
You got it. Someplace there has to be degeneracy, right? I think that was what you're asking. So it's a very, I think it's a very good remark here about his question. So I'm just telling you what I'm going to talk about. Maybe this whole lecture is going to be devoted to that. I don't care. Yeah, it looks not bend. Okay. You take, say, the space of bilinear forms on a vector space. So on something, bilinear forms on a vector space cross a vector space. Okay. Here's 0. Here is a positive definite form. Here are the forms. When you leave positive definiteness, you have to go to degeneracy, right? Maybe here are the negative definite forms. What I am drawing here is an exact picture. These things are cones. Isn't that obvious? If I take a form and multiply it by 27, it has the same signature. It just changes the eigenvalues, right? So these are really cones. So you have the cone of positive definite forms. You have the cone of negative definite forms. You have the cone of signature 3, 1. You have signatures clearly an invariant here, right? So you have, and it's an open condition. Do you understand what I mean when I say it's an open condition? You take the point and you move it in an open set, it doesn't change. You agree that signature is something that does not change by small earthquakes, right? Small hurricanes. Right. Up here in Bremen, sometimes the wind's really heavy, so you maybe go from positive definite to negative definite. But sometimes, okay, you got it? So this is, it's what Avik's talking about is really a non-trivial point. Because if you want to, here it is. You see, here's 0 maybe. And maybe here's this cone here. I'm not drawing very well. All right? Here's the positive cone. And if you want to have a positive definite bilinear form, this thing has to stay in the positive cone everywhere. So this is a non-trivial condition. Okay? A Riemannian metric is a section of the bundle of bilinear forms that is positive definite in the sense that at every point it's in the positive cone. In the sense you pointed out, its eigenvalues are positive. Okay? In the sense that length is positive. In the sense that what we were just talking about, after basis change, it's more or less Euclidean geometry, except you have these different lengths, which are the eigenvectors. Okay? That's what is a Riemannian metric. Okay? Good? Riemann understood the importance of that. And what Riemann understood I think, is associated to a Riemannian metric in a canonical way is a connection. Okay. Let me say it again. Amin gives me a connection. You give, is it right, Amin? Am I saying your name?
Amen.
Iman. I converted a Russian friend of mine's name Amin, and I translated Iman. Sorry. Iman. So, Riemann, you have a Riemannian metric. It's a positive, definite section of the bundle of differential forms, of bilinear forms. Definition. And associated to this is what we call a metric connection. Yes.
Why is it called a metric?
Why is this called a metric?
Does it give
Because, I don't know why, because it measures, for one thing, it measures tangent vectors, or measures vectors in a bundle. I think that's a reasonable thing. It's measuring length and angles. So it's a metric in that sense. The confusing part is what I started with here, that people call this distance function a metric. And I started with that because I wanted to tell you, forget it. Okay, a metric on a Riemannian, on a differentiable manifold is what I just said. It's really a metric on a bundle on a differentiable manifold. The metric on the manifold is on the tangent bundle, of course. Okay. And there's something associated with this in a canonical way. And this thing is what is called torsion-free. Whatever that means. In order to make it canonical, you need this thing to be torsion-free. And guess what? I'm in the manifold. And I'm over here, say, at 0. And I have another point on the manifold x1. And I connect these points with a curve. And everything I just said there has nothing to do with Riemannian geometry, does it? I mean, it's just a point on a manifold and stuff like that, right? Okay. Let's take nabla to be the metric connection, whatever that is. I told you, if you have a curve and a connection, you know how to start here with a vector here, y, and push it parallel. And you end up with a vector here, parallel translate from x0 to x1 of y. Isn't it true? I told you if you have a connection, there's a canonical way to transport vectors along curves. Okay? Take a vector here at the beginning with respect to the metric connection. You have a metric here. Riemann called this bilinear things G. So we have the metric here on this tangent space G x0. Right? I have the geometry of that tangent space. And I have the geometry of this tangent space, Gx1. Now I have something. I have a connection that tells me how to take a vector here, move it along this curve, and get a vector there. Well, if I take take a z here, I'll move it along, parallel transport, use this connection. I get a parallel transport from x0 to x1 along the curve. We should write here gamma, because gamma defines this thing, of z. Now what is the dream here? What is the dream here? I parallel translate by something that's canonically related to the metric. I parallel translate by something that's canonically related to the metric. I take a curve that goes from here outside and goes out into the toilet. Yes?
So you want it not to depend on the curve?
Huh?
So you want it not to depend on the curve?
It'll depend on the curve. Unfortunately, it depends on the curve. That's it, yeah?
But then you want to maintain that the bilinear forms will give you sort of similar things.
Bravo! I don't have any money, but bravo! Did you hear what Abik said? He said, look, this thing, this connection is defined by the metric. I just told you that, I haven't proved anything. Yeah. You use the connection to go to the toilet, and there you can, some curve to the toilet. Unfortunately, or fortunately or not, it depends on the curve. Right? We could go over and have a sandwich and come back and then go to the toilet. Okay? You go to the toilet, right, by this connection. There's another curve that does that, so let's keep a fixed curve, not the one to go to have a sandwich, just a fixed curve. You parallel translate using this canonical thing. You take another thing, parallel translate, you get another vector and so on. What has to be? Is what Abik says, that has to be an isometry. What does it mean, isometry? It means the map. Let me write it down. You take these two vectors here, push them over here. The metric applied to the two vectors here is the same thing as the metric applied to the two vectors over here. Right? That's the word isometry. G x1 of parallel transport from x0 to x1 along gamma of y P parallel transport x1 along gamma of y of z. That's over here at x1 equals g x0 of y z. Now you can see why this subject looks technical. If you would start writing this down in a basis, what that would look like. And that's the reason these horrible Christoffel symbols and this horrible stuff that people make you do, they beat you on the head, they take physicists and make you, bam, 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 it's terrible, right? You don't know what the hell you're doing. You're just making these calculations. Einstein told you how to do that. Isn't that true? It really is terrible. What you are doing is saying, if you take the metric connection, which is canonically associated to the Riemannian metric given to you by whoever, by Riemann. It's not, the metric's not canonical either, by the way. I mean, you have all possible positive definite sections. There are many, many metrics. Yes? There are many, many metrics. But if you take one of them, it's canonically, and then take the canonically related connection, and I claim Riemann had that in mind. Yeah? Then parallel transport takes vectors over there, and this is a statement, is that parallel transport is an isometry. Okay? So, I've gone to about the limiting time. I just want to say the words again that you need to keep in mind. Manifold, tangent vector, vector field. All of that's just manifold stuff. Put these in a bundle. Tangent bundle, that's key. General vector bundles will be important. Why not just talk about vector bundles in general? Okay. Connection. Connection gives you a way of differentiating sections of a vector bundle with respect to a vector field. We will formalize exactly what that is. Notation-wise, that's nabla x, where x is a vector field. That's the thing that differentiates the set. That is a connection. Connection defines parallel transport. It means that if you start at a curve, with a curve, it means start with a vector at the first point of the curve, and you move it parallel along this curve with respect to the tangent vector of the curve. It means that this doesn't change. So it means that a certain nabla, well, it means nabla of the derivative field with respect to this thing doesn't change. This is the right definition of parallel transport. Okay. This transports the vector along the curve parallel with respect to the connection. Okay. The space of all connections is a huge space. We talked about it. You've got partition of unity is some huge space. I will talk about this a little bit about physics. The so-called gauge group acts on this space. And actually, it is of interest to look at this space modulo gauge transformation. Physicists also talk about fixing a gauge. So there are all sorts of words here that are going around. It doesn't matter. You have a huge space of connections, and you're looking for good ones. Riemann found a way of good ones. He said, what I like to talk about is a very natural notion of geometry given by bilinear form. He calls these bilinear forms G. Guess why? Gauss. That was his teacher. Oh, Professor Gauss, I'll need my bilinear form after you. Yes, that's Germany, you see. Professor Gauss. My students never learned that. I have a horrible name, Huckleberry, nobody would call this. Gauss has a great name, Gauss. So G for Gauss. At each point, it is a bilinear form. It is positive definite for Riemann. For Einstein, in elementary relativity, is not positive definite. It has one negative eigenvalue, right? So for Riemann, it's positive definite. And there is a canonical connection associated to that. It's called the metric connection. And the wonderful thing is, parallel transport by the metric connection is an isometry. Yeah. Okay? Now, I will repeat this lecture tomorrow, but with detail. Okay? Thank you.